Happy New Year. I'm Diane Sayre, president of the LaRouche organization, and I'm joined today by Jason Ross, one of the leaders of LaRouche's science team, formerly known as the basement team. And we're about to have the first in what will be a series of discussions about science, and most importantly, the method of knowing whether something is true or not, which is going to be extremely important in the upcoming period as the United States moves out of a catastrophic Biden administration and hopefully into a new and improved era under President Donald Trump, but I will say not without a great deal of work from the citizens and associates of LaRouche. So I'm not going to say more. I'm going to turn it over to Jason and he can tell you why this is important and what he is working on. He's just completed a book on the correspondence between René Descartes and Pierre Fermat, who had very different ways of approaching questions of the physical universe and knowing whether something is true or not, or even bothering to show whether something is true or not. So, Jason, glad we're here together. Go ahead.
Thanks, Diane. So the importance of getting an inside view of the scientific method is something that LaRouche emphasized was necessary for anyone to really be an economist. Because what's the central aspect of economy? What makes an economy function? Why do we have economies and animals don't? The answer is that we are able to discover universal principles. We use our senses, but those principles are not anything sensory. And with these universal physical principles, we transform our relationship to nature, improving our living standards, our potential population on this planet and beyond. And it's therefore the scientific approach that really opens up new eras in economics, new eras in human history. So let's actually hear a clip from Lyndon LaRouche on this subject.
Well, the great obstacle to understanding all of this is, in a sense, elementary. The false assumption is that mankind is bounded by death. And that's the false assumption. This has implications, especially when you come to the human being, who is the only creature which presents the solution to this question. And that is, the common belief is that the imagination working within society creates ideas, and then when the person dies, the idea ends. That's the mistake. You could take the case of the human species as distinct from all other species. And the human species is the only species which has a willful role in history. That is to say, death as an act of a mortal death act does not limit the implications of the outcome and influence exerted by mankind as a living creature. Where does creativity lie? It does not lie in what most people think. It lies in the ability of the living individual to create states of existence, that is, the design of states of existence, to forecast what is going to happen. And that's the most precious thing for me. I grasp that. That's everything for me. And that's what we should hope for. Now, the error is the person says that when you die, you end. Well, that's not quite true. If you are a creative person, you are introducing conceptions which the rest of society did not have. And therefore, you keep doing that. And that's how history is made.
So we're going to apply this in the specific case of Pierre Fermat and his discovery of a principle that became, in today's world, the universal principle of least action, or stationary action, which is the most fundamental physical principle that exists. And it began with Fermat. So Pierre Fermat, he was born in the early 1600s in France. He was a government official, sort of a combination of legislator and judge. He did work in number theory. His famous last theorem was just proved in 1994, so it took over 300 years between Fermat noting it and it actually being, very thoroughly proved. With Blaise Pascal, another French scientist, he did a lot of work on geometry and created probability theory. All of the idea of expectation and so forth, this comes out of letters between Pierre Fermat and Blaise Pascal. He also made big advancements in mathematics itself. He developed a general method of finding the maximum or the minimum in all sorts of circumstances and also finding tangents. This brought him into a dispute with Descartes, who thought that he knew everything there was about algebra and geometry and the union between them. And Fermat bested him in many ways. But the topic we're going to take a look at today is Fermat's work on light. So let's take a look at examples of what the problem was that he was trying to solve. So you've observed, I suspect, that if you put something in a glass of water, a straw, a knife, something like that, it looks like it's broken. It looks like it bends. We can see, as we see it through the glass, it looks like it bends, and then in the water, it's just in a different place altogether. Maybe a more extreme example is this, whatever happened to this duck here. This is a real photo, and this is an example of refraction.
You're sure that's not two ducks?
Or
Or two half ducks?
Well, I didn't take the picture, but
Okay.
so it is possible. It's possible, okay? I didn't go to the zoo and get that one. So the question is, what's happening? Why does light change its path? So in the 1630s, the great René Descartes, who you may have heard about and who was really not that great, this is the guy who's famous for saying, I think, therefore I am. He, in 1637, wrote a book that pulled together his whole method of thought, which he thought was brilliant and was a gift to the world that he wanted to share. And to show how great his method was, he applied it to a few different fields of physics, and one of those was light. Descartes gets credit for his 1637 book being the first one to give a formula for how light bends. Let's hear a little bit about how Descartes explained his theory of light. So this is from the source book here, The Battle for Light, Fermat versus Descartes. So here's Descartes. He says, there is no need for me to attempt to say what light's true nature is. And I believe that it will suffice for me to make 2 or 3 comparisons which aid in conceiving it in the manner which seems to me the most correct to explain all of its properties that experience has made known to us, that we've observed. In this, he says, I will be imitating the astronomers, who, although their assumptions be almost all false or uncertain, nonetheless, because they agree with many observations that they have made, nonetheless allow the derivation of many very true and quite certain consequences. So Descartes' admitting right here, he doesn't really care whether his explanation is right or not. The only thing is, does it match with experience?
Well, also, how does he know that what he observes then, because he observed 2 straws and 2 ducks, actually isn't 2 straws and 2 ducks? He seems to be taking that for granted.
Well, yeah, he does believe that the straw isn't really breaking, in the water. I mean, basically what happened was after he had written this book or after he'd come up with this formula, he had friends who tried it out. And they made very careful experiments. And it looked like what he had was right. So he's basically saying, if the results are good, then my method of thought must have been right.
I see.
So,
but who cares why?
Well, there we go. But so here's how he explains, he gives analogies to explain light. He says, I won't tell you what light is, but I'll use some analogies to help you understand my conclusions about it. So he says, light is like the cane of a blind man. As soon as you tap something, you feel it. Similarly, light goes instantly to our eyes from whatever we're observing. He talks about cats shooting light out of their eyes to be able to see things at night. Descartes uses examples of wine leaking out of holes in the bottom of a vat, and he uses a lot of tennis balls. Let's see the picture of a couple of, these are the kinds of things Descartes' using to help explain light. Obviously, a wine vat has a lot to do with light. And the little man there with the tennis ball, so Descartes makes a lot of use of this tennis analogy, and we'll see how selectively he uses the characteristics of actual tennis balls. So how does Descartes explain light? So first up is reflection. Light, when it bounces off a surface, reflects back at the same angle that it came in at. And he says, well, the reason for that is that if the light tennis ball was just moving right along this way, it never would have touched the surface. So that motion won't change.
Can't argue with that.
Okay, yeah, don't you dare. He wouldn't like it. He says the downward motion, well, that hits the thing, and so the only thing it can do is come back up. So when you put those together, you know, it keeps moving horizontally the same, and then it goes from going down to going up. That's his explanation. Let's take a look at a picture of this. So here's to read Descartes' thoughts. We can conceive that the motion of the ball, which is going from A to B, is composed of two others. One causing it to descend from the line AF down toward the line CE, and the other at the same time causing it to go from the left, AC, to the right, FE, such that these two combined direct it toward B along the straight line AB. And then it is easy to understand that the impact with the ground can only prevent one of these two determinations, and not in any way the other. For it must prevent that which causes the ball to descend from AF towards AC, because it occupies all the space below CE. But why would the ground hinder the other motion, which causes the ball to advance towards the right, seeing as the ground is in no way opposed to this direction? I'll let you think. You seem like you're not that enthused about this explanation. But wait, there's more. Okay, because when it gets to refraction,
and I always hated tennis anyway. So.
Oh, okay. Well, all right. So now, Descartes has to explain how light bends when it goes into water. So at first he says, well, maybe this tennis ball, instead of bouncing off the ground, it's going through like a net or some cloth that it breaks through, and that might slow it down. So let's take a look at what happens if that occurs. So the motion is composed of two. If you look up at the top, there's the ball that's just moving horizontally, and it doesn't change. That's the determination to go to the right. If you look at the downward motion, it slows down. Only the downward motion. Because Descartes says if it never hit the surface,
it would just continue.
It would have just continued. And therefore, even when it does hit the surface, the motion to the right just continues.
Right. But not at the same speed.
At the same speed.
At the same speed.
He says because if it only moved to the right, it never would have hit the surface.
Right.
And therefore, even when it does hit the surface, it wasn't the motion to the right that caused it to hit the surface. And therefore, even when it breaks through and punches through this net, which slows it down, it cannot slow down the motion to the right because it never would have touched the surface if it was only going to the right.
I see. So it arrives at some distance to the right at the same speed as it would have before.
Exactly, yeah. It doesn't really make sense. Now, the only trouble with this is if you compare the path that light was going in that example, it's bending the wrong way. When light goes from air into water, it goes more downwards. So Descartes says, no problem. We'll just make light speed up when it goes into water. So let's see that. Oh, so now the vertical motion is speeding up.
So now he's saying that even though there's some kind of obstacle in the downward direction, rather than impeding it, the obstacle is causing it to go faster.
He's saying light goes faster through water, even though, nothing actually does.
Right.
Like if you actually hit a tennis ball at the water, it's not going to speed up. If you launched a cannonball, it's not going to speed up when it hits the water. So it's kind of a crazy thought, but remember what he said, as long as we get the right results, Who cares? They're just analogies. And again, even though the tennis ball goes faster in water, the motion to the right does not change, because if it had only moved to the right, it never would have touched the water.
I think that you said that before.
Yeah, okay. So here's how Descartes explains the change. He says, let us consider that the ball, having first been impelled from A towards B, is impelled anew, once at point B, by the racket, CBE, which increases the force of its movement by, for example, a third, such that it traverses the same distance in 2 moments of time that it earlier traversed in 3. I'm not making this up. Descartes actually published this in a book that he thought would show everyone what a great genius he was. He really did it. Okay. So Fermat gets a bootleg copy of this book. Descartes wants to publish it. He's got to send it to the administration in Paris to have it approved and for copyright and whatnot. So the government minister in charge of all of this, he gets the book. He does not like Descartes. And so he sends copies of it to some people to get some, negative publicity right off the bat, let's say. He sends a copy to Pierre Fermat. Fermat reads this, and he's not impressed. The kind of things that we were just talking about make up a lot of his objection. And he said, well, Descartes says something that's possible, but he doesn't say why it would actually have to happen. And he doesn't agree with the way he breaks the motion up, and then it doesn't change, the horizontal doesn't change when you go into the new thing. Fermat, he doesn't like that. So he writes back, and Descartes gets wind of what Fermat thinks about his great work, and Descartes is not happy with it. So here's how Descartes responds to the criticism. He says, I have been informed that someone finds some things in my book objectionable. He has doubted one of his axioms, Descartes. But I am convinced that he, Fermat, formed this doubt because he thought I doubted it myself. And because I included these words on page 8, line 24, quote, for it is quite easy to believe that the inclination to movement must follow the same laws as motion itself. He thought that by my saying something is easy to believe, I meant only that it is plausible. In thinking this, he has strayed from my intention, for I consider practically false anything that is only plausible. And when I say that something is easy to believe, okay, what does it mean, easy to believe? I mean that it is not only probable, but rather that it is so clear and evident that there is no need to bother myself with demonstrating it.
Wow.
Yeah.
That sounds like John Brennan.
So
I don't do evidence. Remember that?
Right. So, there's Descartes. He had an enormous ego. And his reasoning just didn't make sense. So that's really all he could do with it. So Fermat believed that what happened was that Descartes actually had his formula from some other means, and he made up this reasoning to be able to have something to write in his book to explain where the formula comes from. Fermat says, I will prove that the author has accommodated his medium to his conclusion, of whose truth he was already certain. And this is something that Gottfried Leibniz, who created the calculus, and also Max Planck, who developed quantum theory, they both look at this example and they say that, well, Descartes stole the formula from Snell, a Dutch scientist. Descartes was in the Netherlands, and that he made up the reasoning to get the formula that he knew because someone else had found it out. I think that's true. So the only trouble was that the formula works. Descartes' formula does work, even though that reasoning is pretty terrible.
Right.
So is that good enough, or is there something else that we should demand of science and knowledge?
Well, if that's the end of everything, I guess you could leave it at that, but hopefully there's more work to be done. I mean, what if you wanted to actually use this principle, then you should probably know what it is, it would seem to me.
Yeah, or if you want to extend it, right? Because something like this, these bizarre analogies, how far they extend to other fields, who knows, because none of them are really controlling or compelling to begin with.
Right.
So
it certainly doesn't make any sense that there's a universal principle in one domain which doesn't apply. It's not universal in that case.
Yeah.
Yeah.
So, as a matter of fact, so Veritasium recently did a video on least action. And when he was talking about Fermat's discovery, he just said that although the formula was known, no one had explained it before Fermat. That's the kind of thing that people say to be too nice to Descartes, because Descartes thought he had explained it, and he published the book with this terrible thing. So
Right.
let's move on. So the matter just sort of stayed there for 20 years. Descartes died. Fermat didn't really do much on light in the meantime. And then in 1657, a friend of his wrote a book on light, and he sent Fermat a copy. So Fermat's friend, he explained reflection, saying that the angles aren't equal because of bouncing balls, or even because the angles should be equal at all, but for a reason that goes back to Hero of Alexandria, who was a 2nd century Greek mathematician living in Egypt. So let's take a look at this. This is how Hero of Alexandria and Fermat's friend explained why light bounces at equal angles. So light's going to go from A to C. And then we've got this mirror down here at BE. Actually, let's go ahead and use the video of this, the next one. Great. Okay, so there's the mirror. Here's the 2 points. Light's going to go from the red point to the blue point. Let's say it takes some imagined path. Let's say it goes from A and it heads to the right to point C and then goes up to point B. There's a total distance that the light has traveled, that length AC plus the length CB. Well, if you mirror B and put a B prime down below, that length AC CB prime is the same as the length ACB.
Right.
Now let's imagine this point L in the middle. Well, not in the middle, but actually it is in the middle in this case. Now, if we just look at the B prime point, ALB prime, this is a straight line. There could be no shorter way between getting between those 2 points than this one. And that when you consider the mirror image up top, that's why the light goes from A to L to B. The equal angles are a result of a more general principle that nature wants to take the path of least distance, that nature makes the simplest action.
That's interesting.
What do you think? Is it possible for nature to, does this sound like it's giving nature a goal or an intention? I mean, does this make you uneasy? What do you think about this idea?
Well, I think it would actually be much more alarming if things were arbitrary. Like if you threw a stone and you had no way of predicting where it was going to go, for example, or you shone a light and where it went was different from one time to the next. I think that would be much more alarming than the idea that there's a reason or a direction or a certain principle to the motion.
That would be alarming. I guess well, let's see where he takes this. So Fermat reads this book and he thinks it's fantastic. And he writes back to his friend and he says, if you let me join some of my geometry to your physics, we will accomplish a work of collaboration which will put us in defense against Descartes and all his friends. First, I recognize with you the truth of this principle, that nature acts always along the shortest paths. But he says that refraction, it doesn't seem to take the shortest path because it goes, it bounces out, it goes a longer way. So what do? Well, here's the solution. Fermat says we can extricate ourselves from this difficulty by assuming, with you and with all those who have treated this matter, that the resistance of the media is different, and that there is always a certain ratio or proportion between those two resistances when the two media have particular consistencies and are uniformly composed. So Fermat says that light isn't taking the least distance, it's going to take the least time, or the path of least resistance. He phrases it either way, partly in deference to his friend who thinks that light moves instantaneously. Descartes thinks it actually does have a speed and that it slows down in the water. No one had measured the speed of light at this time.
I thought Descartes thought it sped up in the water.
Descartes thinks light speeds up in the water, and Fermat thinks light,
Slows
like
down.
everything else, would slow down in the
Okay.
water. Yeah.
Yes. Okay.
Yeah. So they take different approaches there. So the question is, how do you find the exact spot? If light's going to go from one point into the water to another, how do you find the exact spot where it goes from the air to the water so that the time is the least? Well, Fermat does have a general technique for figuring out maximum and minimum problems, but he does not apply it right away. In fact, it takes him 5 years before he does the math. So he has the idea of least time. He doesn't know what angles it will create. He can't test it with an experiment. It's a hypothesis at this point, just a hypothesis. Now, let's see what the Cartesians thought about this hypothesis. Now, René Descartes was dead, but Claude Claircellier was compiling all of his letters to publish in a book, and here's what he said to Fermat. He said, "The principle that serves as foundation for your demonstration, namely that nature always acts by way of the shortest and simplest paths, is a moral principle only, and not at all a physical one, which is not and could not be the cause of any effect in nature. It is not a physical principle because it is not this moral principle that makes nature act, but rather the secret force and virtue that is in all things. And it could not be the cause of any effect in nature, because otherwise we would assume nature to have knowledge. And by nature, here we mean only that order and that law established in the world as it is, which acts without foreknowledge, without choice, and by a necessary determination." So I think in response to what you had said earlier, Claircellier, the Cartesians would say, well, yes, it's, sure, we don't want a ball to bounce, arbitrarily if you hit it, or you throw a rock and it goes in a loop. But the only way to understand it is with this secret force and this virtue, which sort of makes a decision, not makes a decision, which has a next moment to a next moment to a next moment. For them, time can only go forward. And here's Fermat saying that the result is guiding what comes before it.
Right. Well, it's interesting also that he says morality. You're saying this is moral, and that can have nothing to do with physics, which reminds me of Henry Kissinger saying that he never mixes morality with politics, which is, it's peculiar, but also ironically very insightful, although he didn't realize he was being insightful, because there is a process in the universe of development, and things that cohere with that thrive, and things that reject it, we do have the free will to reject it, don't do so well. So that's a very interesting question, which is maybe for another time, which is how do you define morality?
Well, I think that's something let's come back to that, because I want to talk about this in the context of credit and monetarism too. So Fermat, after a few years, does do the math, and he figures out the path that light takes if it takes the least time. Let's take a look at this video that shows in a thumbnail what Fermat's method is. So the dark path here, these are supposed to be like little arrows here. The dark path is the one that light actually takes. It's the path of least time. And you can see that the light moving on that path reaches the final point before all the others. Now, if you take a look at the two outer ones, they both reach the blue point at the same time at the end. Or if you take a look at the second one from the edge on either side. So Fermat says, hey, there's if you don't have the best answer, then whatever you found out has a twin. There are two paths that have the same non-optimal time.
I see.
And his technique is to say, well, let me take these pairs that have the same amount of time and pull them together until they coincide, and that's how I'm going to find the path of least time. So that's what he does. And let's hear what he finds out. So Fermat writes to his friend who had written the book before, on New Year's Day, so New Year's resolution, January 1st, 1662. As soon as I attempted to take up the analysis, I had two obstacles to surmount. The first was that although I was sure of the truth of my principle, which is that there is nothing as probable or apparent as the assumption that nature always acts by the easiest means, nevertheless, he was advised on all sides that the experiments accord precisely with the proportion of refraction of Descartes, and that even though his demonstration is faulty, I feared that it would be useless for me to attempt to introduce a proportion different from Descartes', and that the experiments that would be made after I had published my invention would be able to destroy it on the spot. So maybe he wants to keep it a hypothesis. He delays testing it because he might find out that it doesn't work, and Descartes seems right. The second obstacle, he says, is the length and difficulty of the calculations. He says that he freed himself from the first obstacle by my knowledge that there are an infinite number of proportions, different from the true one, which approach it so closely that they could fool the most able and exact observers. It's possible to have a formula that's so close it might look right without actually being the truth. Now, here Fermat is perfectly paralleling Kepler. Johannes Kepler, the first modern scientist who figured out the motions of the planets, he was trying to break out of the mathematical approach to astronomy. The approach of, hey, it doesn't matter if your model makes sense as long as it puts the planets in the right place on the sky on the right night at the right time. That's all that matters. Kepler created a mathematical model that worked extremely well. Very, very well. But he also reasoned that just because it looks right, that's not enough to say that it's true. Even if observation can't tell the difference, there could still be one. Also, this is another note about Kepler. So Fermat's method of maxima and minima was included in a textbook that someone else wrote, and he included a chapter on Fermat's method. In that same math book, which Fermat refers to and clearly knew about, the author wrote, Kepler, the wisest of modern astronomers, did not accept any kind of hypothesis that saves appearances, but wanted simple hypotheses in accord with physical causes. So this is the Kepler influence here. So what does he do? So here's Fermat. I proceeded by virtue of obedience, as the monks say, in carrying out your orders to do the calculations, and I worked out the whole analysis according to my method. The reward of my work was the most extraordinary, the most unforeseen, and the happiest that could be. For after having run through all the equations, multiplications, antitheses, and other operations of my method, and having at last solved the problem, I found that my principle gave exactly and precisely the same proportion of refraction that Descartes had established. I was so surprised by such an unexpected outcome that I had difficulty coming out of my state of astonishment. I repeated my algebraic operations many times, and the result was always the same. Even though my demonstration assumes that light passes through dense bodies slower than through rare ones, an assumption which I find quite true and indisputable, and yet Descartes assumed the contrary. What must we conclude from this? Would it not suffice for the friends of Descartes that I leave him in free possession of the theorem? Will he not have enough glory in having known the actions of nature at first glance and without the aid of any demonstration? So it's a compliment that's an insult. Right. He says, I even add in favor of Mr. Descartes that the great truth of nature did not dare stand up against his great genius, and that it let itself be taken and discovered by him without being forced to do so by a demonstration, like a fortified castle, which, although otherwise strong and not easily conquered, nonetheless surrenders based solely on the reputation of the attackers, without even waiting for the cannon to fire. So he says this in some of his later letters too, that Descartes should take the credit for having discovered it, and it's even all the more impressive because his explanation made no sense. So therefore, we should really honor Descartes. He's so smart. So I think the fun thing about the relevance of this today gets at one of the things that you had brought up a little earlier about intention and about nature having a course that it's going to go on. One of these things that comes up in economics all the time is about, can the government do anything right? There are people that say the government shouldn't pick winners and losers. The government definitely shouldn't pick losers. I agree with that part of it. But there's this idea that if you try to apply reason to an economic process, something bad will happen. This is like the free market approach. And there's some areas where you don't want, the government doesn't need to be particularly involved, but you have to have an intention on the biggest things. And I think if we look at examples like the space program, the nuclear research program, the development of nuclear power, these are things where the government played an enormous infrastructure, obviously, the New Deal projects. These are areas where you have to have an idea of what you plan to have a generation or two down the line, and then make your policy accordingly. And it's this almost religious-like fanaticism to say, no, it's individuals trying to maximize their profit that creates a good for everybody. That tension reminds me of what Claire Sellier had to say about Fermat, saying it can't be a principle. There's no such thing as intention.
Well, it's what Lynn said at the beginning, because how do you forecast? Is it just happenstance, and what does that mean? And also what they're looking at, because these experiments are not someone coming with a flashlight, if they had them in those days, shining the flashlight at a particular angle and then saying, I know where it's going to go. But you're looking at the beginning and the end and saying, what is the ordering principle? How does it arrive there? And how does light know to get to that point? Because in human economy, it would frankly be pretty catastrophic. It would be really irresponsible of a government to say, well, we're just going to let everyone do what they want, and you're going to buy cheap and sell dear, and whoever sells his product for the least amount of money is going to do very well. And whatever products people want to buy is what's going to be available. So whether it sustains human life, whether there's an increase in life expectancy or any of these other parameters that you think a government ought to be interested in, doesn't matter. It's sort of an arbitrary, we'll just see what happens.
And that's not the way to do things. And if you want to succeed, you have to have these goals. I mean, in your life, in a society, and so I think that this idea that a scientific or physical principle can have the form of an intention, that is still, I think, extremely controversial today, even though physicists, if you say, is the principle of least action universal, they'll say yes, basically. I mean, so they'll say yes, but I don't think that we act as though the universe is governed by intentions. Or sometimes we don't act by our intentions. I mean, people sometimes, you find yourself being pushed around day to day by your impulses or desires or whatnot. This is how, Adam Smith or Jeremy Bentham would say human beings are. You've got your desires and you're trying to satisfy them, and then that guides your life, as opposed to trying to do something.
Right. And that's also, I mean, this is the question that Leibniz kept bringing up. Why is it this way and not otherwise? Why must it be this way? And because it must, does that mean that it has nothing to do with morality or choice? That's kind of fun. I suspect that in here we also will find some of the problems with AI.
I think so. Yeah. Well, that one's definitely for another discussion.
Yes.
But yeah. Well, look, and all of this stuff. I mean, the importance of, the reason I translated this book is because it didn't exist in English. This is one of the most important discoveries in the history of science, and you couldn't read it if you didn't read French. So, this is just part of a narrow path of discoveries that LaRouche identified as being just the highlights, the most important discoveries to look at if you want to get a sense of the internal history of science. We'd talked also about Kepler, who was the first modern scientist. Fermat, Leibniz's calculus looks so similar to Fermat's method of maxima and minima. It's really astonishing when people, when you see what Fermat did and you compare it to Leibniz, it's the reason that Laplace said that Fermat was the real inventor of the infinitesimal calculus.
Wow.
So, it connects with this train of discoveries that we should get more into as well.
There's one other thing, because he makes the point that his when he did all the mathematics, that it worked out precisely, that he knew there was cause. And I'm thinking about Kepler refusing to accept, yeah, it looks like it's right, on the question of circular orbits, for example. And you say, yeah, well, it's off by however many minutes it was of an arc. And that wasn't good enough for him.
Mm-mm.
He said, I don't care if it's, a fraction of a second, unless we can explain, unless you know what the principle is. So you say, okay, it sort of locks in that this is the way it has to be. The approximation does not yield to the understanding of a principle.
Yeah, it's something different. I mean, are you
Right.
talking about perceptions? Are you talking about effects? Are you talking about what's generating them? And LaRouche would often use the analogy of the complex domain, that you've got the so-called real, the projection onto the sensory world or the world of phenomena. And then you've got that, the whole rest of the complex domain, that's what are the principles that are giving rise to these effects. And if your hypothesis isn't in the realm of the complex or in the realm of the imaginary, let's say,
Right.
then it can't be right, because that's where the principles live. So yeah, Kepler said, okay, I've got a math formula that tells me really well where Mars is. It's much better than anyone else. He could have just written a book, put that in there, and everyone would have said, you're the greatest. This guy's fantastic. But that wasn't his goal. He wanted to know what was, he looked at it in terms of he wants to know what God was thinking. How did God set things up? That was the kind of outlook he had. So he didn't think God said, oh, here's a nice formula. No, there must be something.
Let me get my tennis racket.
Yeah, right. There's got to be something simple, a cause. Right. So Kepler had this hypothesis of gravitation. You had talked about the circular and elliptical orbits. People think Kepler just tried out an ellipse and saw that it fit. It's just not true at all. When he was trying to figure out what shape the planets could take in their orbits if it wasn't a circle, he still had to say, well, what's physically causing it to get closer and further from the sun? And he had a whole theory on this. The theory wasn't right, but it shows that he was committed to saying there has to be some physical cause for this. So at a certain point, he even actually finds the ellipse that the planet moves on geometrically. And he says, if I move the point over here, that would match really well. But he has to say, but why would that be? He doesn't let himself get off the hook and just give the right answer. He's got to know that there's a reason that nature gave that outcome. So.
Great. Well, thank you. I think that also explains exactly what Lynn is saying about your life. Is it the two bookends of where you live or die? Or is it something that's enduring and universal? Because where do you locate a principle? We can't put it here on the table so the audience can see it, but it is something that's actually eternal, which we can discover with our mind, and it exists even if we are physically no longer here, which is a very exciting idea.
Yeah. You spend a lot of your life, most of your life, being dead. So you got to...
Funny way of putting it.
Well, it's true.
I guess so. All right. Well, we would hope that lots of people get to spend at least some of their life being alive, which is why these ideas are so important. So this will be continued.
Okay. All right.
Great. Thank you.